Okay, in this video I'm going to tell you how to use the Forces feature in MechDesigner to improve your design. I have prepared a single axis mechanism as a demonstration for forces. Okay, starting at the top, we've got a pusher mechanism which we can imagine pushing a product into a pocket or something with a quick return back to get the next product. The mechanism is driven by a cam rotating at constant speed. The cam follower sits on a rocker which is connected by some links and a bell crank to the pusher tool. The motion design on the left shows the position and velocity of the pusher over one machine cycle. For MechDesigner to calculate bearing forces, motor torques and cam forces, we need to apply loads or external forces which act on the mechanism. First we shall consider forces arising from the acceleration due to gravity and the acceleration of the mechanism parts themselves. To do this we need to add masses to the parts. So let's start simply by adding some mass to the pusher tool. We do this by adding a profile and forming an extrusion. You can also import a CAD part with its mass properties or specify masses and inertias directly by editing a CAD line. Okay, so now we are ready to turn on forces. MechDesigner will start calculating forces when you press this button and display the forces when you press this button. You can control the length of the force vectors by using the spin boxes right at the bottom of the screen. Next, we need to consider the power sources in this mechanism. First, we must look at the kinematic tree to the left of the graphic area. Just clip the tab to display the kinematic chains. If we click on each of the chains, we can see which is which of the two. One includes the camshaft and motor, the other contains the follower rocker right back to the pusher. All the dyads are listed inside the tree. Let's not worry about them just yet, but if you open up the dyads, you will see that all the parts and joints of the kinematic chain are included. Each motion dimension in a kinematic chain must be complemented with a power source or motor. These will keep the inertial and gravity forces in balance. It is important to understand that the motor does not need to be located on the motion dimension, although as we can see this is the default. There is a motor currently driving the pusher, and we need the pusher to be driven or powered by the camshaft motor. To do this, we must change the power source of the pusher from the motion dimension to the cam itself. If we right click on the top kinematic chain, which contains the pusher part, then we can choose to edit the power configuration of that chain from the pop-up. We can see that there is only one motion dimension in the kinematic chain, which we select. It gives us a choice as to which element we can place the power source or motor. We choose the 2D cam. Now we can see that the cam surfing is acting on the roller and the roller is acting on the cam surface in accordance with Newton's third law. So now we have set up our model and can display forces at all positions in the machine cycle. Let's begin, fingers crossed, improving our design. So we could change just about anything to improve this theoretically, but I'm not talking about motion design, so let's just say we are stuck with the motion design. We need our camshaft underling to keep lubrication and dirt away from the product, but let's suppose that we can move our centers a bit and change the link lengths. If we start winding the machine round by dragging the machine clock indicator at the bottom of the screen, we can identify when in the machine cycle the cam force is highest. Sure enough, we see high contact forces during the peak acceleration of the pusher when it's rushing back for its next turn. But we can see the earlier negative acceleration generates more contact force than the later deceleration as it comes to rest, even though both accelerations are equal, albeit of different sign. The clue lies in the bearing force of the follower rocker, which seems extremely high. This tells me that the cam is generating too large a component of force against the bearing in order to generate sufficient force to drive the load inertia. In other words, the pressure angle of the cam is probably high. Okay, I have already set up a design set which I can use to edit the position of the camshaft and see if I can reduce the force when the acceleration is at a maximum. I will move it so that the normal of the flank of the cam aligns with the direction in which the follower can move. In other words, I'm trying to reduce the pressure angle. So now the pressure angle is less at this point and the contact force has come down, so I'm happier. But I'll be happier still if I haven't increased the contact stress elsewhere in the cycle. So let's now run the machine and see what's going on at other points. Okay, this seems a bit better. I have reduced the cam contact force at maximum acceleration, but maybe I can go further. Perhaps I can change the position of the roller on the rocker and see if I can reduce the force even more. Unfortunately, I'm limited on the size of cam I can fit into the box. Okay, right, the next question is, will the roller remain in contact with the cam throughout its cycle? Well, I need to look at the cam contact force direction to find out about this. Now, I've changed the color coding so that the force acting on the cam is in blue, the same color as the cam part. Well, all is well until about here. So we need to add a spring to keep the roller in contact with the cam all the way round, otherwise it will be tapping out a very mischievous rhythm. We could cheat with a groove cam, but no, that would make the cam too big, which wouldn't fit into the box. Let's add a spring between the ground point here and the end of the follower rocker here. Wind the machine round to the position with the shortest spring length. Edit the spring by double clicking on it. And now we can edit the free length of the spring. Give the spring a spring constant. Wind the machine round again and check for the direction of the blue contact force vector. Points in all the way round, and so we have stopped the bounce. We could of course carry on improving this design, but I'm going to stop here.